Starting with the scalar product, which is sometimes called the dot product or the inner product. I like the dot product because you make a product by putting a dot in between and it's easy to remember. Now here we get into some interesting math stuff. There's a reason why we do this. We're going to see some examples of why this works. But we invent some new math, and I'm just presenting the new math to you as a result. So for example, if you had 2, 3 as a point, which you could write as a vector as 2, 3, and you had 3, 5 as a point, then we would say that the dot product of the vector 2, 3, there's 2, 3, and 3, 5, which would be the dot product of 2, 3 and 3, 5 is just 6 plus 15, or 21. And right now that number should mean nothing to you. You're like, wow, that's great. 21. Okay? Now you have to realize I'm presenting you the results of what these things are. What happened for mathematicians is they would have been doing a bunch of math and then said, hey, 21 would sure have been a useful number. And it just keeps coming up over and over again. If you just multiply the x's and you multiply the y's and add them together, then we get something that's going to help us figure out some problems that make it easier than what we used to do when we did sine law, cosine law, all the geometry and stuff that we used to have to do, especially when you get into 3 dimensions. So the dot product in 3 dimensions, same idea. You just multiply across and add them up. So here's our first example. Our one vector is 2 minus 3. Dot product, our other vector, is 1, 2. Multiply the x's, you get 2. Multiply the y's, you get minus 6. Add them together. We have a dot product of minus 4. Try this 3-dimensional one on your own. All right, how did you do? Negative 18? Woo. Fascinating results from the dot product or scalar product. And this is something when you get into higher level math and you start, I don't know if you say inventing, but start using new math, you want to check if some of the old rules of math still hold true. Yeah. You have to go to the dentist. You better go. What reminded you? The word scalar? You think of scaling, teeth scaling? All right. Now, some of these things, you'd be like, oh, that makes sense. Because just like multiplying, 2 times 3 is the same as 3 times 2. That's not true for all mathematics. It used to be that part of the IB curriculum looked at matrices. When you multiply matrices in the wrong order, you'd get different answers. So some areas of math, you're not allowed to do that. But for dot product and for vectors, you can. Same thing if you multiply by a constant out in front. Do you remember the word for a constant in vectors? We call a constant in vectors a scalar, which makes the word scalar and scalar product confusing because you've got scalar in two different parts. Good morning.
Could you please?
Yeah, he already left.
You don't want to leave. Okay, thank you.
I shouldn't have paused it. Okay. So you can multiply that scalar by the first vector, or you can multiply it by the second vector. It wouldn't matter which one you multiply it by. The distribution property holds as well. If you're adding two vectors, you can do the dot product of the first one and the dot product of the second one, and then you wouldn't have to take the time to actually add the vectors, because the dot product always gives you a number. So you get a number here and a number there, and then just have to add them up. And finally, there's the zero vector, which is just the origin, which is just the one that we got before. Uh-oh. And when you multiply by the zero vector, you will get 0. Which should make sense, because if I have 2, 3, and I dot product with 0, 0, I will get 0 plus 0, which equals 0. Now here are the interesting results. Those last ones were just fascinating properties, and these are interesting results. That the dot product comes out to be the same thing as if you squared the vector after you found its distance. Right? When you find its distance, it's always a square root of something. And so when you square it, it goes away. Which should make sense. Again, think what happens when you have, oh, put a dot in there. If you had the same vector and you did a dot product, you're going to get squared plus that squared, which is what you're going to do if you did a squared plus b squared equals c squared anyways. And the most important result is that the dot product of two different vectors is equal to the length of u, the length of v, times by cos of the angle. And what this will do is help us figure out some things that we used to have to use the cosine law before. Now you're going to be able to figure out stuff without having to use the cosine law. So here you have a vector u, and here you have the vector v. This would be the angle theta in between them. And the dot product of these two is the same as the length of this, and the angle in between. Cos of that angle. Now, if you wanted to find out if two lines were perpendicular to each other in the past, you found the slope of one line, you found the slope of the other line, right? And if those slopes were negative reciprocals, then you found out whether or not they were perpendicular. The dot product makes it quicker, because what you can do now is you can find out what is the position vector of any line. So let's say you have the line, I'll do a couple position vectors here just quickly to show you this. Let's say you go to 2, 3, so this vector would be 2, 3. A negative reciprocal, because this has gone over 2 and up 3, right? Negative reciprocal would be flipping that and making it negative. So for example, if I had this point over here, which was negative 2 comma, or negative 3 comma 2, that would be going 3 to the left, 2 up. That would be the opposite, and that would be perpendicular. Look what happens with the dot product. And another thing you can think of with vectors is vectors kind of are the same as slope. Because if I have the point 2, 3, the slope is 3 over 2. Vectors, because they have the x on top, are like the slope just flipped around. Now this vector is going to be negative 3 comma 2, and the dot product is just going to be negative 6 plus 6 equals 0. So now any time that you get a dot product equal to 0, because of this important result, sorry, clarify that one. Because of this important result, and the fact that we know that cos of 90 is equal to 0, that the only way the dot product can be 0 is if theta is 90 degrees. Now, when the angle between the vectors is less than 90, because you know cos in quadrant 1 is positive, if you get a positive answer for your dot product, you'll know the angle between them is less than 90. If the angle between them is bigger than 90, that would be like having an angle in quadrant 2, and cos is negative in quadrant 2. So then you would have the dot product becoming equal less than 0. So if your dot product is negative, you know your angle is bigger than 90 degrees. If your dot product is positive, you know you have an acute angle. And if two vectors are parallel, the angle between them would be 0. So if you have two vectors that are parallel, and if you would draw them tail to tail, so if I redraw that first blue one and then start my next green one right on top of it like that, the angle between those two would be 0. Then what the dot product is going to do is it's going to be exactly the same as if you took the length of one of them and multiplied it by the length of the other one. And with the dot product, if we rearrange that formula, and this is probably the most powerful result, and the thing that makes vectors very useful and quick to solve things, is rearranging that result. We can find the angle, because cos theta is always the dot product over the length of one and the length of the other one. So just think back to the math you had before this. Let's take a point here, 5, 1, and draw that line segment. And let's take another point here, 1, that doesn't look like 1, that looks like 2, 7, and draw that. How would you figure out that angle? With a protractor. Go back. We're going way back. So like all the math that I've learned, just measure it. You could do maybe sine law or cosine law, because you could make a triangle here, right? And if you did a squared plus b squared equals c squared, you could figure out this length and this length. You couldn't use SOHCAHTOA because it's not a right angle triangle. Okay. You would know those two sides, but you don't know the opposite side, and you don't know the angle. You usually need 3 things in order to use sine law or cosine law. My point is it's not necessarily that easy using the math that we used to have. could be done, but it's not necessarily quick because you'd have to figure out a bunch of side lengths and you'd have to figure out a bunch of angles. Okay? Another way you could make right angle triangles, you could make a right angle triangle here and a right angle triangle there and get new, this would be one theta and this would be another theta, theta 2 and theta 1. And theta 2 minus theta 1 would give you theta. That would be another way that you could do it. But look at how easy this is going to be now. This vector is vector 2, 7, and this vector is vector 5, 1. Okay? Cos of theta, if I do the dot product of these, it's going to just be 10 plus 7. 2 times 5 and 1 times 7, 10 plus 7. Underneath, the length of each of them, well, the length of this one is just 1 squared plus 5 squared will be root 26. And the length of this one will just be 4 plus 49, which is root 53. And you've got a ratio for cos, and you can do cos inverse of that ratio. (17 over root 26, root 53), and you have whatever theta is. Yep. No, because the dot product will, 2 times 5 gives you 10. And then 1 times 7 gives you 7. And the dot product, you'll always add them up. So. And that was just imagining it in 2 dimensions. This question says, now we have something in 3 dimensions. We got an angle going this way and an angle going that way. How do you find the angle between those? And whereas our 2-dimensional one, when we looked at it on paper, would have been like, ooh, we could do that, but it might be a little bit hard. Right? If you tried to draw this one, it would be really hard. But the dot product works for this as well. You want to find the angle between. We'll do the dot product of V and W. And then the length of V and the length of W. I should have made this one a B, because then it could have been BMW. Yeah. Unless there's anybody here whose Spanish is the first language. Because in Spanish, people that learn or are Spanish speaking, they can't tell that there's no difference between a B sound and a V sound in Spanish. They're the same. You can say it either way. Like a cow is vaca, or you can say vaca. Either way. Doesn't matter. Anyways, interesting fact of the day. Dot product, did you get 12 plus a negative 2 plus 2? And for the length of V, 9 plus 4 plus 1. And the length of W, 16 plus 1 plus 4. Over square root of 14 times the square root of 21. So do cos inverse. What do you prefer, radians or degrees? Okay, we'll do degrees. You get 45.6 degrees to 3 sig figs. Oh, look at those squiggle brackets.